How's it going, everyone? This is Team EagleLi, sponsored by EaglePicher Technologies. Today, we will be presenting the improvements made to the BMRS, Battery Management Research System. Specifically, we'll be talking about the creation of the new DC discrete load, also known as Pablo. These are our technical directors. They helped guide us throughout the creation of our project. Daniel Wartz on the left is a senior systems engineer at EaglePicher Technologies, and on the right we have Brendan Moore, who is a software engineer. This is our team. On the left we have myself, Brendan Lorena, the one computer engineer for the project, and on the right we have the three electrical engineers for the project, starting with Benjamin Feeney, Peter Martin, and Adam Inabtawi. EaglePicher Technologies is a leading American company that provides cutting-edge battery and energy storage solutions for various industries, including defense, aerospace, medical devices, and more. The company was founded in 1843 and is headquartered in Joplin, Missouri. EaglePicher offers a wide range of products and services, including lithium-ion batteries, thermal batteries, custom battery packs, battery management systems, and more. They also provide engineering services to help their clients design and develop custom solutions that meet their unique needs. The company has a long history of innovation and has been involved in several notable projects, including the batteries used in the Apollo mission, landing missions, and Mars exploration rovers. Today, EaglePicher continues to push the boundaries of what is possible in battery technology, working to develop efficient and reliable solutions that can power the devices of the future.
In a world shaped by ever-growing need for enhanced technology, batteries are the backbone of what fuels such technology. In recent years, engineers have developed a lithium-ion battery, which is more efficient and sustainable than the regular battery. The problem with these types of batteries is that they are unpredictable. Having the ability to predict when a cell is deteriorating is almost impossible. If not properly charged or discharged, they can cause injuries or even fatalities. Our vision is to create a better testing platform to replace the commercial battery management systems that are limited by their sensor accuracies and find new ways to make batteries last longer and safer for the consumer. Our anticipated best outcome is to improve last year's battery management system by implementing new and improved components such as our cohort main focus, the programmable discrete load. We believe by replacing the pulse width modulating programmable load that was used by last year's cohort with our new resistive discrete load, our collected data will improve since a DC load will more accurately represent a resistive load hooked to a battery compared to a pulse width modulating resistive load. Regrettably, we have not achieved our intended ABO. However, we have made significant progress that would enable future cohorts to achieve this goal. We have successfully developed a prototype of a low-channel discrete load that operates as intended, and have created a comprehensive Altium project for the discrete load system, which includes schematics, footprint and symbol libraries, and a designed and routed PCB layout. Furthermore, we have developed a functioning GUI application that enables remote interfacing with the discrete load using a built-in Raspberry Pi. Overall, we have not achieved our ABO. We have made significant strides in developing and optimizing the discrete load system, providing a strong foundation for future teams. Over the year, we have had a lot of technical accomplishments. Some of those accomplishments are creating a full desktop application for Pablo the discrete load, created a discrete load specification sheet, designed full PCB schematic and layout for the discrete load in Altium with a schematic library and a footprint library for the project, and we developed an automatic fan control using temperature sensors. The best outcome for this project would provide EaglePicher with an improved functioning battery management research system that can run live tests on lithium-ion batteries. The economic impact for this project would be a massive success for battery safety. Lithium-ion batteries are some of the best batteries on the market, though when put under too much stress, they can become very dangerous. Economically, the goal for the Battery Management Research System is to help prevent disasters involving lithium-ion batteries. This is Adam Anaftawi, and now I will discuss in more details my personal technical accomplishments for this project. Highlighted on the block diagram is my area of focus, which is creating the Ultium PCB design for the 8 channels, cooling aggregate, and fan. During the program, I was in charge of the Ultium work for the Pablo discrete load. I worked on creating the Ultium schematics and created component schematic symbols and footprints for the picked components for the project. I also added 3D models to the components to more easily visualize the PCB layout and align the components. In addition, I created a footprint and a symbol library for all 73 components used in the project. The high-power resistors and MOSFETs in the discrete load project generates a significant amount of heat, which needs to be properly dissipated by being attached to a cooling aggregate. To address this, I designed a PCB layout that accommodates for all the high-power components requiring cooling by attaching them to the picked heatsink. In addition, I positioned the heatsink to allow a designated airflow route through the board to cool surrounding components using convection cooling. I was in charge of routing all these components together to ensure that the discrete load functions properly.
How's it going, everyone? My name is Brendan Lorena, and today I'll be talking about the software aspect of the project as well as additional contributions. During the first semester, we worked on the discrete load prototype, and I also worked on the prototype software for the discrete load. First, I created a console-based application that can detect, control, and configure individual ports for digital output on the USB 1208FS Plus. This is the MC Computing GPIO device that we were using to control the 8 channels on the discrete load. After creating the console-based application as a proof of concept, I began to adapt the application into a full GUI for effortless controls of the 8 channels on the programmable load. I also assisted in researching areas of improvement for the AMBATS platform, as well as familiarizing myself with each of its various components. Upon successful testing of the discrete load prototype in the first semester, in the second semester we decided to create the fully fledged product and software. One of the big changes we made this semester was deciding to switch GPIO devices. We switched to the Raspberry Pi Pico. The reason why we made the switch was because it was much more user-friendly and it made it much easier to integrate with the other components of the new discrete load. The first thing I did was create a software concept where I showed all the screens that I was going to integrate into the fully fledged software application. I also created an SRS to highlight the requirements set by the team and by the TDs. My goal for this application was to create a modern GUI where the user can create load profiles and communicate with the new discrete load. This is the main menu. The main menu prompts the user with 3 options, the first being the quick session. The quick session brings you to the session screen where the user can type in a load value and control the discrete load on the fly without any planning for quick testing. The second option is the new profile. This will bring you to the new profile screen where profiles can be created. The third option is the load profile button, and this will load an existing profile into the session screen. This is the profile setup screen. The user will have to enter a profile name and session name. Next, the user will have to create some steps. Each step comprises of a current value and time value. The current value will be loaded onto the battery cells for the amount of time specified, starting from the first step to the last step. Steps can be added and subtracted in rows depending on how many steps you want and how long you want the profile to last for. The collection of steps is what makes up the load profile. If start session is clicked, Then these steps will be sent to the Raspberry Pi in order to turn on each individual channel specified by the profile. If the Save Profile button is clicked, then users will be able to save the profile they just created to any folder on their desktop, depending on what they want. The file name will automatically default to the profile name entered in the text box. Also, these profiles can be retrieved from the main menu screen by clicking on the Load Profile button. Error handling and shortcuts are essential to the functionality of the program. My program offers quick navigation. This allows for users to tab from one text box to the next in order to create quick data entries. Error handling has also been added to the program in order to prevent crashing if an invalid input is entered by the user. Automatic input validation and correction is another big feature of the program. Due to the hardware limitations, users can only enter a current value from 0 milliamps to 12,000 milliamps with a 40 milliamp resolution. If an invalid input is entered into the text box, then the program will automatically round to the nearest valid input and enter correct units. Input shortcuts can also be used for quick entry. The user can use the S, M, and H units in order to automatically format time inputs. Current values can be entered in either amps or milliamps. If left blank, then the program will default to milliamps. The entirety of the GUI application was made using C#. In order to communicate with the Raspberry Pi Pico, I had to use a serial connection. In the profile setup screen, the user has to enter the current value for each step. The current value is then converted to an 8-bit binary string. These strings are sent in order from the first step to the last step to the Raspberry Pi Pico script. The Raspberry Pi Pico script is written in Python, and it takes the 8-bit binary string and then turns on and off the GPIO ports accordingly.
Hello, my name is Benjamin Feeney, and today I will be talking about my technical accomplishments for this project. I will be discussing the construction and testing of the prototype load channel to prove the concept, along with how I designed the resistor arrays for the full power product, along with the Raspberry Pi Pico pin assignments to interface between the software and the hardware. My first major technical accomplishment is designing and constructing the prototype load channel in order to prove the concept of the final product. I first started out by selecting the necessary parts in order to get the desired values for the low power channel. Next was to take those parts and construct it on a breadboard, and then hook that breadboard up to benchtop supplies in order to test the performance. And once the performance was confirmed to be exactly what we needed, we moved it over to a soldered board in order to get a more permanent solution. My next major technical accomplishment was selecting the high power resistors needed for the full product channels. These resistors would need to come in a TO220 or TO247 package in order to be mounted onto a heatsink. The Ohmite T EH100 series of resistors was selected for the high power channels 5 through 8 due to their very high power dissipation rating and large size in order for efficient cooling. I selected the Catic Electronics MP900 resistors for the low power channels 1 through 4 due to their smaller package size but still high enough power dissipation rating and heatsink mountable design. My final major technical accomplishment was assigning the pins of the Raspberry Pi Pico to their desired functions on the discrete load. These include using the analog to digital converters for measuring temperature and current, and attaching GPIO extender modules in order to have enough pins for all the necessary functions, such as indicator LEDs, display drivers, and channel control.
Hello everybody, my name is Peter Martin, and today I will be talking about my technical contributions towards this project. As seen in the block diagram, I highlighted what I've been working on through the year, that being the temperature sensor, the front panel, and the power rails for the discrete load. My first technical contribution that I would like to share with everybody was the creation of a temperature sensor for fan control, which can be seen by the circuit to the right. The reason we wanted to add this feature was due to the fact that the cooling aggregate we had selected had a 50% margin of error on the power that was being outputted. Due to this, we didn't want the fan to be running at 100% at all times, which would reduce the noise being outputted by the system. The temperature sensor we decided to go with was the TMP01 ESZ, which was an internal temperature sensor. This sensor allowed us to set certain thresholds, which we chose to be 27 and 55 degrees Celsius. 27 being the low threshold and 55 being the high. I also added a differential amplifier using the op-amp 177, which would scale the analog output from the temperature sensor from 5 millivolts per Kelvin to 10 millivolts per degree Celsius. These measurements would then communicate back to the Raspberry Pi Pico, which would output a pulse width modulation to a bipolar junction transistor, which connected to the ground pin of the fan, which would reduce the speed of the fan using the PWMs. The fan would ultimately come connected to the cooling aggregate, which required 24 volts. Due to the make of the fan, we had to add a flyback diode to be in parallel with the voltage and the ground pin of the fan, so that the fan wouldn't burn out when running. Since this temperature sensor is an internal sensor, we decided to place it underneath the cooling aggregate with a thermal gap pad in between the sensor and the aggregate. Another technical contribution that I had made came with the design of the front panel. The front panel would be key in allowing manual input to the discrete load, as well as indicating what is on and what is off. The block diagram on the screen shows how each component selected interfaces with the Raspberry Pi Pico and the discrete load. The diagram on the left of the dotted line shows components ranging from LED indicators, push buttons, a rotary encoder, a USB to A connector, a remote and local switch, as well as a display. As stated by Ben earlier in this presentation, we were in need of serial extenders for added GPIO pins. And the diagram on the right of the dotted lines shows how two of our toggle switches connect to the system itself. The enable toggle switch connects to the output of the 8 channels, which allows the current to flow to the lithium-ion batteries. The second switch is an emergency switch, which will be, when enabled, will cut power to the entire discrete load. The next slide shows the front panel layout, which can be seen to the right. This layout shows how all the components will mount onto the Metcase front panel that we plan to order. The Metcase front panel was 132 millimeters by 269 millimeters with 4 cutouts to connect to the met case enclosure. The components on the conceptual drawing are not drawn to actual size, but with the measurements that we had conducted, we found that all components will fit onto the front panel. The display that we had found ran at 5 volts, and the Pico GPIO pins ran at 3.3 volts, so I had to implement a level shifter for both devices in order for them to communicate with each other. In order to connect the front panel components to the PCB, we also needed certain key connectors, which I had found, and these were all created by Molex. I had also started to work on the drill guide for all the components, which would be 3D printed and then align with the met case front panel to manually drill holes into the aluminum panel that we had ordered. The final technical contribution that I would like to talk about today was the implementation of the power rails. Early on in this project, we had specified that our discrete load would draw AC power from the wall outlets. Due to this, I had done research on certain AC to DC converters and linear voltage regulators. With this research, I had found 2 separate AC-DC converters that would help our efforts. The first being a 3-port AC-DC converter that outputted 24 volts, 5 volts, and 12 volts. The second was a 2-port AC-DC converter that outputted positive and negative 15 volts. This 2-port AC to DC converter was specifically for the op amps, as they required a negative voltage input. The block diagram to the right shows how all components which require power are given power. The 8 channels that we had created required 2.5 volts as the input voltage, so I implemented a 2.5 linear voltage regulator that would require 12 volts to output 2.5 volts, as well as a 3.3 linear voltage regulator that required 12 volts of input, which would then output 3.3 volts. We would now like to take this time to acknowledge 5 influential individuals who have been outstanding mentors throughout this year. First, we would like to thank our amazing technical directors, Daniel Wartz and Brandon Moore, for all their support. Throughout the year, they have provided tremendous guidance in preparing us for the real world and providing us with an amazing project. Their experience and expertise in their respective fields has been a key factor in the development of the discrete load. We cannot thank them enough for their leadership and guidance. Next, we would like to thank Dr. Harish Sunak for giving us this amazing opportunity to showcase all we have learned throughout our time at the University of Rhode Island. We would then like to acknowledge our consulting technical director, Brendan Smirback, for his guidance and his former experience with the Capstone program. Finally, we would like to thank Dr. Zhang for his generosity in allowing us to work out of his electronics lab throughout the year. So thank you to those 5 individuals.